Welcome, ladies and gentlemen, to my video on the basic ideas of cryptography. In this video, I want to introduce you to the basic ideas and applications of modern cryptography without getting into technical details. I assume that you have some interest in computing and are familiar with the basic terminology, for example, what bits and bytes are or what an algorithm is. There will be a little bit of math in this video, though I try to keep it to a minimum, but at some points I will just need it if I want to illustrate certain things. It is not necessary to perfectly understand all of it. It is just to provide a rough idea of how things work. So here's an overview of what I will be showing you. First, I will introduce the meaning and applications of modern cryptography, at least the most important applications. Then two such applications will be presented in more detail, which are encryption, where messages are turned unreadable for unauthorized persons, and authentication, which ensures that the person you think you are talking to is really that person. As an example where these ideas are brought together, I will then quickly discuss the transport layer security protocol, which is the basic basis of security of the modern internet. Then in the fifth part, I will show how the security of cryptographic schemes can be derived theoretically, at least in some slightly idealized sense. And finally, I will discuss the impact of quantum computing on current cryptography and what approaches there are to deal with it. As usual, please like this video and subscribe to my channel to help me produce more content. And I also want to point you here to my second YouTube channel, MathFlix, where I publish comprehensive courses on mathematics at a university level. Please subscribe to this channel as well. Now, what is cryptography? The word cryptography is composed of two classic Greek words, kryptos for secret and graphein meaning writing, so the secret writing. And originally the term cryptography meant the art and science of making texts unreadable in such a way that only the intended recipient would be able to decipher it. So an authorized person can take the unreadable text and transform it back into the original text that we wanted to send. And in this video, I will usually refer to these texts as messages. And in the modern day digital communication, the meaning of cryptography is broader as it used to be. So it encompasses the classical meaning of encryption, which, as before, is to make messages unreadable for everyone except authorized recipients. Then another important aspect is integrity, which means the ability to verify that a message or data has not been tampered with. And thirdly, digital signatures and non-repudiation. So these are two sides of the same coin. This is to provide methods to prove your authorship of a message, but also to make your authorship undeniable so that other people can be sure that it was you who sent a message or signed some document. Now, in everyday language, the word code is often used for an encrypted message. But in technical terms, in engineering terms, code has a more restricted meaning. And it actually has a different meaning than this casual use. It just means that a message is brought into a suitable representation for transmission. But it does not imply that the code is in any way made unreadable to unauthorized persons. So for example, code could simply mean that we put some message into binary code. So we describe it through a sequence of zeros and ones, but it does not say that we want to make this message secret. And for practical reasons, it's actually usually easy to recover the original message from the encoded message, because it was not, when we encode something, it was not our intention to make it unreadable. So we just want to bring it into a convenient format, and usually we also want to have a convenient and quick way to revert it into the original representation. So when we encrypt a message, the resulting unreadable text will be called a ciphertext. So that is what we call a text that is only intended to be decipherable to the intended recipient. And the original unencrypted message will be referred to as the plain text. So we take the plain text, encrypt it, and then we obtain the ciphertext from that. And usually our messages and ciphertext will be binary encoded, because we assume we're doing everything on a classical computer. And yeah, these bit sequences we use for the binary encoding have a certain length. And so bit sequences of length L, the set of all of these sequences, will be denoted by B to the power of L. So I use this hollow B for bit sequences. And bit sequences of arbitrary length will be denoted by B star. Now let's look at the scenario that I will always assume when talking about cryptography. We must assume that communication happens via a public channel, for example, the internet. And we have two parties here, the monkey and the elephant, who want to exchange messages. And they have to do this through this public channel. Now first, assume the monkey has a message, M, that he wants to send to the elephant. So there's a message space, which I denote by this curly M, which contains all the conceivable messages M that one might send, and a ciphertext space, this curly C, containing all the possible ciphertexts derived from the messages in this message space. Now, in the next step, the monkey takes the message and encrypts it and obtains a ciphertext C. So the sender encrypts the message M, and there's some encryption function, which I call enc, which maps the space of messages to the space of ciphertexts. And applying this encryption function to our message M yields the ciphertext. Now the ciphertext is now sent via the public channel to the recipient, to the elephant. And the recipient now uses a decryption function, DEC, to map the ciphertext back to a message. So the elephant receives the ciphertext, and then she decrypts the ciphertext with DEC to obtain the original message. And since we use a public channel here, an eavesdropper can listen in on the channel and, in theory, steal the ciphertext from the channel. And of course, the idea is now that the encryption should be so good that this ciphertext is of no use to an unauthorized eavesdropper. Now I want to make the case for public cryptographic algorithms. So if you look back in ancient times, simple encryption schemes usually worked by substituting letters by other letters in the alphabet. And the security of these methods relied on two things. First, keeping the method of encryption secret, and second, that fast computation and good statistical methods to break the encryption either by brute force or by analyzing the occurrence of letters in the ciphertext were not available. However, modern cryptography adheres to what is called Kerckhoffs's principle, and it's stated as follows: the security of an encryption scheme must not depend on the secrecy of the encryption algorithm, but may only depend on the secrecy of a key. Now, what do we mean by a key? A key is some input parameter for the encryption function that is unique for every participant in the communication. And so what are the advantages of Kerckhoffs's principle together with the use of keys? Firstly, keeping algorithms secret is much harder than just keeping a simple key secret. And if a secret algorithm gets compromised, you have to come up with a new algorithm. And encryption algorithms usually are difficult to come up with, so that would be quite a hassle. Whereas if the secret key of one of the participants in the communication gets compromised, you can still use the algorithm. You only need to generate a new key that replaces the compromised one. Also, it's much easier to build secret communication systems for more than two participants if everybody can use the same algorithm, and you only have to generate different keys for each participant. And a very important aspect is that public algorithms can be tested by more people, and thus flaws are discovered more quickly. So, for example, the National Institute of Standards in the United States uses a public tournament to determine new standards for cryptographic algorithms, and so the candidates are made publicly known, and very often due to this process flaws are found in the candidates for possible standard algorithms. And yeah, that's actually the last benefit, which is also a very important one. Open systems facilitate standards, so having a publicly available cryptographic algorithms makes it easy to implement certain standards in software that all participants can adhere to. Now, cryptography has a certain place within the IT security landscape, and it's not the only thing that security depends on. When software is not implemented securely, then cryptography can be circumvented by an attacker. So the attacker doesn't even have to try to break the cryptography, but can simply get around it by using some other flaws in the software. For example, logical flaws or unexpected side effects in programs can be exploited to give access to a system or to manipulate data in it. A classical attack is through so-called buffer overflows, where deliberately malformed input data for a web application or some other application that can be reached via the internet can allow the execution of code on the victim's machine. And in SQL databases, when they accept, or when some web front app and accepts unchecked input data, input queries for SQL, then so-called SQL injections might reveal arbitrary entries in the database, which could be passwords that could be then further exploited by an attacker. Or these injections might even allow code execution on the victim's machine. And similarly, in cross-site scripting, an attacker tries to manipulate the HTML code of a website in order to read sensitive user input, such as passwords, for example. In addition to that, in addition to the technical flaws, social engineering is nowadays the biggest attack vector. So this involves manipulating people into revealing their passwords, or manipulating people into giving an attacker physical access to sensitive systems, or some other manipulation of the human side of computing to gain an advantage. Now let's take a look at encryption mechanisms. We distinguish two main approaches to cryptography. The first is private key cryptography, where two communicating parties use a shared secret key for encryption and decryption. Because both use the same key, this is called symmetric cryptography as well. And the second approach is so-called public key cryptography, where every party in the communication has its own pair of keys, one public key and one secret key. So the public key is used for encryption and the secret key is used for decryption. And because of this, it is also called asymmetric cryptography. We begin with the private key encryption. So here we have two communicating parties again, and they share one secret key K that both of them use for encryption and decryption. Again, the situation is that our monkey wants to send the message M to the elephant via this public channel. What the monkey does, he encrypts M using K, the shared secret key, to obtain the ciphertext. The ciphertext then goes through the public channel, is obtained by the elephant, and the elephant uses the shared secret key K to decrypt the ciphertext into the original message. And then the communication goes on, and if some time later the elephant wants to send a message back to the monkey, now the message is called M prime, this could be a different message than to the first one, then the elephant uses the shared secret key K to encrypt M prime, gets a ciphertext C prime for this one, sends it back through the channel to the monkey, and the monkey uses the shared secret key K to decrypt C prime into the original message M prime. And an eavesdropper monitoring the public channel can read out all the ciphertexts that are sent here, C and C prime. But the idea of private key encryption is that as long as the eavesdropper cannot get his hands or tentacles on the secret key K, there's no way the encryption can be broken. Of course, that assumes a decent encryption scheme. Before communication with private key encryption can happen, the secret key K must be shared between the users, and this can happen in various ways. For example, they could exchange the keys in person if they know each other in person and can meet. Or otherwise, they could use a public key method to exchange the secret key. This is more feasible if there are multiple users involved that might not be personally acquainted to each other. And the commonly used private key encryption schemes are all based on similar principles. So the input message, M, which is assumed to be given in a binary encoding, is split into blocks of a fixed size. And the actual encryption then works on each of these blocks, blockwise, by permuting, shifting, and applying some arithmetic operations that in some way involve the secret key K to the bits in a block. And the decryption method is very similar to the encryption. And nowadays the most common private key encryption algorithm is the so-called Advanced Encryption Standard, AES, which operates on 128-bit blocks. And so it chips up the message into 128-bit blocks and operates on each of these blocks. And the secret key could be of length 128, 192, or 256 bits. The advantages of private key encryption are that it's easy to implement, it is well researched and tested, it's very fast compared to public key encryptions, and the arrival of quantum computers will not affect its security in a significant way. The disadvantages are that the security of the currently implemented private key schemes is not mathematically proven, but it is supported by years of research and scrutiny. Another disadvantage is that keys must be exchanged between any pair of users. And for communications with many users, many keys need to be generated, exchanged, and stored. And storing keys might be a security risk, because if someone manages to steal a stored key, then the encryption can be broken. And these disadvantages can be remedied by using disposable session keys, which can be shared using a public key method. So you don't store the keys, you just use them for a short time, and once the communication session is over, they get thrown away. Okay, let's look at public key methods now. In public key encryption, every participant in the communication has a pair of keys, P and S, where P stands for the public key, which is known to everyone, and this is used for encryption. And S stands for the secret key, which is known only to the user who owns it, and this one is used for decryption. So here's how the principle works. The elephant, as a participant in the communication, generates her own public key and she generates her own secret key. And then she broadcasts her public key through the channel. Now, if the monkey wants to send a message M to the elephant, then what happens is the monkey can use the publicly known public key of the elephant for the encryption scheme and inputs his message M there, and out comes the ciphertext. Now the ciphertext is sent back through the public channel to the elephant, and the elephant now takes her own secret key, which is not known to anyone except for her, for the decryption method, puts in the ciphertext she received, and out comes the original plaintext, the original message M. Now here the idea is that if properly implemented, the encryption is unbreakable as long as the secret key S of the elephant here cannot be obtained by an attacker. So if the eavesdropper monitors the public channel, well then the ciphertext can be found and the public key of the elephant is known anyway because it's public. But to decrypt it, to decrypt the ciphertext, the secret key would have to be known, but this one is not available to anyone. It was never sent over the public channel, so the eavesdropper cannot decrypt the obtained ciphertext C. In practice, every public key algorithm relies for its security on a difficult mathematical problem. So what we do in very broad strokes is to encode the plaintext as some integer number or as an element of some complicated algebraic structure, such as a group or a ring. So if you don't know what that means, that's okay. It's not really required for this video, but just so you've heard the terms, if you want to look into that further. Well, then the encryption function, depending on the public key P, applies some mathematical operation to the plaintext. And for this, the public key is used. So this operation in some way depends on the public key. And in this way, the ciphertext is computed. And in a similar process, the decryption function DEC is applied to the ciphertext and uses the secret key S as an input parameter. The security of this encryption scheme relies on the decryption function being practically impossible to compute without knowing the secret key S. Currently, the most common public key encryption algorithms are RSA, named after its inventors Reeves, Shami, and Edelman, which uses modular arithmetic over the integers for encryption and decryption. So modular arithmetic is where you consider the remainders of integers, and it's like counting time on a clock, for example. And its security is based on the difficulty of computing the prime factorization of large integers. And currently, the keys P and S are usually of size 2048 or 4096 bits. And the other commonly used algorithm is Al-Gamal encryption, which uses the arithmetic in finite groups. So a group being some mathematical domain where you can perform arithmetic operations, which usually is a bit more complicated than in the integers. And one class of such groups that is very popular for cryptography are the so-called elliptic curves. And these groups are used for encryption and decryption. And the security of this method is based on the difficulty of computing the so-called discrete logarithms in certain groups. So discrete logarithms means reversing exponentiation. And here reasonable key sizes depend on which group is used. So for elliptic curves, they could be between 384 and 2048 bits. To get an idea how a public key encryption algorithm can work, we look at a naive version of the RSA algorithm. And I say naive because in practice it would be not implemented this way. It would be a bit more complicated to make it truly secure. But for a general understanding, this naive version is good. Now the following secret data is written in red to make it a bit easier to follow along. And this does use some math, and it's okay if you don't really know the math and fully understand what's going on. Just want to give you an idea how such a cryptographic algorithm can look in principle. And I will not explain why this method works, because that would be far beyond the scope of this video. Now the situation is as usual. The monkey wants to send a plain text message M to the elephant. The elephant picks two secret large prime numbers, P and Q, and computes their product N. Then the elephant picks randomly some number E co-prime to the product P minus 1 times Q minus 1. So co-prime means E and this product here they have no common divisor other than 1. Then the pair N and E, so this E and this product N here, together are published as the public key for the elephant. The secret key of the elephant is determined by finding some number D that satisfies E times D is congruent to 1 modulo this product P minus 1 times Q minus 1. So this means if I take the number E times D and divide it by this number here, then the remainder should be 1. And the D satisfying this property is the secret key. And it is in fact the case that such a D always exists. Now, if the monkey wants to send the message M to the elephant, he encodes the message as an integer modulo n, so Z index n denotes the set of integers modulo n. And the monkey encrypts this message as follows. The map going from Zn to Zn by taking M and taking the exponent by E. So E is part of the public key, so that's known to the monkey. So he can compute this exponent, and he takes this exponent modulo n. So after computing the exponent, the remainder modulo n is taken because the arithmetic happens in Zn. Now the encrypted message C, which is obtained in this way, is sent to the elephant. To decrypt this ciphertext C, the elephant uses her secret key D, this number that was obtained here, by this property. And this again maps the modular integers mod n to themselves. And the ciphertext gets mapped to C to the power of D mod n. And this works because the decryption applied to C is actually, because this is C, is the decryption applied to m to the power of e. So this is actually m to the power of e times d. And because we are computing in modular arithmetic, in Zn, this is the same as the original message m. Okay, so now there is quite a bit of knowledge about modular arithmetic involved to understand this. So if you've never heard of modular arithmetic, then it's perfectly okay if this doesn't make any sense to you. But it is a good motivation to learn more about modular arithmetic. Go to my math channel for that. Now, the advantages of public key encryptions are that the secret keys never need to be shared with anyone, which makes it easier to keep them safe. So recall that in private key encryption, the two parties involved in the communication both needed to have the same secret key, so that it had to be shared in some way. Also, public key encryption is usually mathematically provably secure if we assume the difficulty of certain mathematical problems. And it's more versatile than private key encryption. For example, we can also use it for digital signatures and authentications, but more about that in a minute. The disadvantages are that it's much slower than private key encryption. And the second point you can also turn on its head and say it's provably secure only if we assume the difficulty of certain mathematical problems. And unfortunately, we don't always know this difficulty for sure. And the encryption schemes that are currently in use are significantly affected by quantum computers. Now, the efficiency disadvantage can be remedied by combining public key and private key methods. So we will see this in the TLS example later. And to deal with the quantum security or insecurity, we actually have to devise new public key algorithms that are not affected by quantum algorithms. And I come to that towards the end of this video. Now, since we talked about using public key methods to exchange secret keys for private key encryption, let's look at one method to do this. So the obvious way would be simply to encrypt the private key using a public key encryption scheme and send to the other party, and then use the more efficient private key encryption from that point on. This requires that the two parties have exchanged their public keys beforehand, though. And another popular method is the so-called Diffie-Hellman key exchange, named after its inventors, Diffie and Hellman. And it does not require prior exchange of public keys. Again, secret data in this algorithm is written in red to make it easier to follow. So here the situation is the monkey and the elephant want to generate a shared secret key K over an insecure channel. How do they do that? First, well, they use this standardized Diffie-Hellman protocol, and that requires that there's some standardized generator G in some cyclic group. So recall a group is just some domain where you can perform arithmetic operations, similar but usually more complicated than the integer operations. And there's some preferred element in this group, which we call G, which is called the generator. And this one is publicly known, so it's part of the protocol. Now, the monkey chooses a random number A and computes G to the power of A, which we call X. And then X is sent to the elephant. And the elephant does exactly the same thing. She chooses a random number B, computes the generator to the power of B, we call this Y, and then Y is sent from the elephant to the monkey. And now both of them can compute their shared secret. So the monkey computes K equal to Y to the power of A. So recall A is secret, but the monkey knows it. So the monkey can compute Y, which he got sent from the elephant, to the power of his own secret number A to obtain G to the power of AB and uses this as the secret key. And the elephant does a similar thing. She got sent X by the monkey and she knows the secret number B, which only she knows. So she can compute X to the power of B. And this is also G to the power of A times B, which is the same as what the monkey computed. So they both obtain the same secret key K. And now they can use K as their shared secret key. And note that in this protocol here, K was never actually sent over the insecure channel. Now, in practice, usually this K is not directly used as secret key, but there's a so-called key derivation function which derives some secret key from this K to make it more secure. But the main principle is what we showed here. And in order to break this, you would have to be able to determine B or A from one of the elements X or Y. And that is the so-called discrete logarithm problem. And this is expected to be very difficult. Now we discuss authentication, and we cover two aspects of authentication. First, message integrity, to check if data was tampered with. And second, identification of participants in a communication. Authentication can be used both with private and public key methods. We've already learned about encryption, which is the classical task of cryptography, both in the private key and public key setting. So here it is again, the public channel, the monkey encrypting a message, sending the encrypted message through the public channel and it being decrypted by the elephant. And here we have our eavesdropper who can listen to the public channel and obtain the encrypted message, but hopefully not the plain text. But even if the attacker cannot break the encryption, he might still be able to tamper with the encrypted message, which is called a man-in-the-middle attack. So our octopus, the attacker, reads out the encrypted message C and somehow modifies it and then puts the modified encrypted message C tilde on the public channel, and this gets delivered to the elephant and decrypted to a plain text M tilde, and perhaps the elephant doesn't notice it. Encryption does not protect against message tampering. That's important to understand. So when this happens, in the best case, the manipulated message M tilde is just gibberish. So the elephant will not understand what this even means because the attacker here didn't really know what he was doing. So C tilde is just some modification of C that decrypts to some gibberish message, and probably then the elephant will notice that something is wrong. But in the worst case, it contains falsified data that will not be noticed by the recipient. For example, if M was not intended to be human readable data anyway, or elephant readable data in this case, then the elephant might not notice that something is wrong with the tampered message. For example, if M contains numerical data. Now, message tampering cannot be prevented, but we can create a signature from the message M that can be verified by the recipient, so at least we notice when a message has been tampered with, even though we can't prevent it. This is as follows. So we need a signing function, sig, that computes the signature from the message. So we apply our signing function to the plain text M and obtain the signature sigma. And then we send sigma together with the encrypted message, C. After decryption, the recipient can use a verifier function, ver, with inputs M and the signature sigma. And this returns true if indeed the signature of M equals sigma, and it returns false otherwise. Now, the idea is that for two distinct messages, M and M tilde, the signatures have to be distinct. So if sigma is the signature of M, then it must be different from the signature of the tempered message M tilde. First, we consider private key methods for message integrity. So when used with private key encryption, the signing function SIG uses the shared secret key K as an additional parameter. Now, very broadly speaking, the signing function works by applying a cryptographic hash function to a sequence of bits obtained from the message M and the key K by some arithmetical operations. And such a cryptographic hash function, H, is a function that has the following properties. H maps bit sequences of arbitrary length to bit sequences of a fixed length L. And it is a so-called one-way function, which means that if we have the output B, which is a bit sequence of length L, then it should be practically impossible to compute some pre-image, to compute some bit sequence X such that H of X equals to B. Okay, so from the hash alone, it should not be possible to find out which data gave rise to this hash. Also, it should be collision-free, meaning it should be practically impossible to find two distinct bit sequences X and Y of arbitrary length such that they compute to the same hash, so such that H of X equals H of Y. Now, such pairs XY with distinct X and Y may exist, but it should be so unlikely to find these that it's practically impossible. And there are several cryptographic hash functions in use today. Among the most common ones are the SHA-2 and the SHA-3 function, which is for some reason also known as Ketchak, or however you pronounce that. I have no idea what the word means. And they allow for different hash length between 224 bits and 512 bits. Some older hash functions, such as SHA-1 and MD5, which are not quite up to standard anymore security-wise, but they are still used for less security-critical applications. For example, when you download a file, and sometimes you get a hash with that file, and once you've downloaded it, you can compute the hash on your own machine and compare with the one given on the website to make sure that no errors occurred during download or that you didn't get a manipulated file. Now, how does this work in practice? Here we have again the monkey who wants to send a message M to the elephant. And what we do now, the message M is put into the signing function that depends on the shared secret key K, and it spits out sigma, the signature for M. And then the encryption is applied to M and sigma combined. So we just attach the signature to our plaintext message and then encrypt what we get out of this. And that gives our cipher C. Now it's important to note that here M and sigma both go into the encryption function, but in other schemes it might be handled differently. So sometimes M is encrypted first and then sigma is attached to the cipher, or sometimes sigma is actually computed over the ciphertext and not the plaintext. So there are different versions of this, so I'm just going to show you one of them for simplicity here. Next, the ciphertext is sent through the public channel. The elephant receives the ciphertext and now decrypts it using the shared secret key and obtains the plaintext message and the signature from it. And now both plaintext and signature are plugged into the verifier function, which again uses the shared secret key, and it spits out true to confirm that this is indeed the message that the monkey sent, because it would be just too unlikely to have a correct signature if the message had been tampered with. An attack now looks like this. So the eavesdropper or the attacker, the octopus, reads out ciphertext C and places some manipulated ciphertext C tilde on the channel. This is received by the elephant. It's decrypted to some fake plaintext M tilde and wrong signature sigma tilde. And because those two don't match, the verifier spits out false. So now the elephant knows, okay, I don't have the correct message, something's gone wrong. Maybe there was an error in the transmission, or maybe someone manipulated the message. Now we consider public key methods for message integrity. So if our participants in the communication already have their public and secret key pairs, then those can be used to generate a signature for the message. So we can use the same keys that we use for encryption also for the signatures. Now, what happens? The sender of a message signs the message using his own secret key S prime as an additional parameter. So the signing function for the plaintext message uses the secret key of the sender to obtain the signature. And the receiver then verifies the signature using the sender's public key P prime as additional parameter. So the verifier depends on the public key of the sender and gets as input the received plaintext and the received signature. Now observe that for authentication we use the public and private key of the sender, whereas for encryption, if you recall, we used the public and private key of the receiver. And the common public key encryption algorithms such as RSA or El-Gamal can be used with little modification to sign and verify messages. So here is how it works. Both participants, the monkey and the elephant, have their public and secret keys, P and S for the elephant, P prime and S prime for the monkey. Now, the monkey uses the signature function with his own secret key to generate the signature. Then the monkey uses the public key of the elephant, which was broadcast before, so it's known to everyone who is on this network. The monkey uses the public key of the elephant and the message to encrypt it and obtain the ciphertext, which then is sent through the public channel. Now, the elephant uses her own secret key S to decrypt the ciphertext, which gives her the plaintext message and the signature. And now she uses the monkey's public key, P prime, which also was broadcast over the public channel, so it's available to everyone. She uses this public key, P prime, to verify the signature and the plaintext message. And if everything went correct, she will get true. And again, the attack would be the octopus, our attacker, listening to the ciphertext, modifying it and sending the wrong ciphertext. Decryption would then yield a wrong plaintext and a non-matching signature, so the verifier would return false. And beyond verifying message integrity, public keys can be used to uniquely identify users in vast networks. So this brings us to digital signatures. And this can be used when sending emails or controlling access to network resources in financial transactions, or to prevent users from denying authorship of a message later on. The question is, how do we obtain a user's public key and at the same time can trust that it really is this user's key? So this is something I glossed over before, but now we can talk about this. To obtain trusted public keys, we need a trusted certificate authority, CA, with a well-known public key, P index CA. So here again we have the monkey and the elephant, and I will show you how this works. And note here we have the hamster, and the hamster's wearing a fancy hat. This means that the hamster is a respectable person and therefore well suited to serve as our trusted authority. And here the hamster has his own secret and private keys as well. In the first step, the elephant identifies herself to the hamster, so that may happen in whatever way. Maybe they know each other personally, or maybe the elephant has some physical document to prove her identity. So this is not specified any further in the protocol. Once the identification has taken place, the elephant sends her own public key for certification to the certificate authority. And then the certificate authority uses its own secret key to generate a certificate. So this certificate contains information about the identity of the elephant and that P is indeed the public key belonging to the elephant. Then the certificate is sent back to the elephant, and now the elephant can use it by publishing her public key together with the certificate. This gives everyone the chance to use the public key and at the same time verify that it's really the public key of the elephant. Now, the monkey can do this as follows. So he takes the publicly available certificate, which was signed with the secret key of the certificate authority, and now he can use the public key of the certificate authority to verify the certificate. And if the public key in this certificate matches the one that the elephant published, then the monkey knows indeed that this public key belongs to the elephant. The most common format for digital certificates is the X509 standard. And just as an example here, it's to give you an idea what a certificate contains. This standard demands that a certificate contains information about the version of the standard, then a unique serial number for the certificate, the algorithm that was used to generate the signature, information about the certificate authority, validity dates for the certificate in case it has an expiration date, information about the person or institution whose certificate has been certified, the actual public key, so that's the information we need most from it, and possibly some further information about it, and perhaps some additional information for extensions of the X509 format. Now, there are some problems with the concept of a trusted certificate authority, as you might have guessed. So there's the authority issue, as I call it, that any organization can only know so many people whose identity it can confirm. So nobody can confirm the identity of every person on the planet. And it also happens that certificate authorities have been compromised and have issued certificates to the wrong person or organization. So for whatever reason, it could be malice, fraud, or that they've been hacked. And there's trust issues. It is unthinkable that any certificate authority will be trusted by everyone in the world. So their certificates will be useless when communicating with someone who does not trust the certificate authority. And to deal with these issues, one has to accept that there are multiple specialized certificate authorities, and each of them provides certificates for a particular context. In the end, you still have to trust someone, and usually that is the software providers that give us our operating systems or browsers, because the certificate authorities are usually built in the operating system or the browser. So Apple, Microsoft, Mozilla, Google, this really trustworthy group, provides you with a list of certificate authorities in their products. Then there are technical issues, which can arise when certificates that are made to identify users are used for access control, and they might not provide sufficient information for that. And then certificates have to be combined with an access control list, which complicates the system and possibly introduces additional points for attacks. And this can be dealt with by modifying the certificates to refer to permissions rather than individuals. Expiration issues. It must be possible to take a certificate out of circulation if a user gets hacked or loses the permission or the permissions attached to that certificate. And for the expiration of certificates, there are some more or less satisfactory solutions, such as databases for revoked certificates that you can look up when you receive a certificate and verify if it's expired or not. Next, we look at the transport layer security protocol, which is an interesting example that brings together the concepts that we discussed so far. And the original internet protocols were designed without built-in encryption. And the Transport Layer Security Protocol, TLS for short, was invented to provide encryption for any internet traffic. So usually when you go to a website in your browser, you use the HTTPS protocol, which is TLS combined with the classical HTTP protocol. So it's very rare that websites nowadays are addressed with HTTP, and that's not very secure anyway, so it's not a good thing if there is still a website like that, and usually your browser will show you a warning if that happens. And this TLS protocol is not application specific, so you can use it with practically any internet service such as HTTP, email, or any other service where a client communicates with a server. In the TCP/IP protocol stack, if you know about that, it is located on top of the transport layer, where TCP is located, and beneath the application layer. It was originally developed under the name Secure Socket Layer, SSL, in 1995, and due to security problems through its different versions, it underwent several major changes until it arrived at the current version TLS 1.3, which has been around since 2018. And more precisely, we should call TLS a protocol suite, because it's not just one protocol, it includes several protocols. The most important ones of these are the TLS handshake for establishing encrypted connections, and the TLS record protocol, which specifies how the data is sent. Let's have a quick look at these protocols. The TLS record protocol specifies the format of the data packets used in TLS during the handshake and the subsequent data transfer. And it's actually quite a simple format. So we have a segmentation in different bytes with different meaning. So the first byte, type, gives information about the data that's being transmitted. So whether it's handshake, or if it's encrypted data, or if it's an alert. The second and third byte have the values 3 and 1 for historical reasons, so there's no particular meaning to that. Then the next 2 bytes, the data length field, simply contains the length of the following data field. So the data field can contain up to 16 kilobytes, and how much it is precisely is given in the data length field. And for the handshake, the data field is unencrypted, but afterwards, once the handshake is complete, this is where the encrypted data is stored. Now the TLS handshake is the heart of the TLS protocol. It uses certificates and public key methods to verify the server and create a secret key for the following private key encryption of the communication. And of course, the handshake uses the TLS record protocol to encode its data. So we'll show you a somewhat simplified version of the procedure for the TLS handshake, so you get the general idea of how it works, but I will not explain every little detail. The setting is that the client initiates communication with the server and requests encrypted communication. In the first step, the client generates a random number A and computes some public information G to the power of A from a public generator G. So this is as in the Diffie-Hellman key exchange, for which we will actually use it. Then the client sends the client hello message to the server, and this includes the just computed G to the power of A and a list of supported private key encryption algorithms. The server then also generates a random number B and computes a publicly available value G to the power of B, and then computes the Diffie-Hellman shared secret G to the power of A to the power of B. So recall the Diffie-Hellman procedure, where we derived a shared secret for both parties in this way. And from this, the server derives the secret key K. Recall that I mentioned in the Diffie-Hellman algorithm that we don't always use this directly as the secret key, but somehow derive the secret key from it. And this is what happens in TLS. Then the server replies with the server hello message to the client. This includes the just computed G to the power of B. Then it also has information on which private key algorithm the server chose from the list given by the client. It includes the server's certificate and a signature of all this previous information here for the client to verify that the message is not corrupted. Now the client then verifies the server's certificate by contacting a certificate authority, so that now the client is sure that he or she is really connected to the server that he wants to be connected with. And then the client also computes the shared Diffie-Hellman secret and also derives the shared secret key from it. Now the client sends the change cipher suite message to the server to indicate that now the encrypted communication can begin with the private key method that they just agreed on before and the secret key that they both derived with the Diffie-Hellman procedure. The server replies with the change cipher suite message to confirm the encrypted communication, and this concludes the handshake. Now all subsequent data that is being sent will be encrypted with the chosen method and the shared secret key. If at any step here something goes wrong, then the connection is terminated. The TLS protocol currently supports several algorithms for private key encryption. There are several versions of the advanced encryption standard and also a method called CHA-CHA-CHA-20. The shared secret key K is only used for the current communication session, and for future sessions a new shared key is derived. And this way we can ensure forward secrecy in the TLS protocol, which means that even if an attacker can compromise one session, that is, find the secret key K for that session and decrypt the communication, it is not possible to decrypt any past or future sessions with that key, because different keys were used and will be used in different sessions. And I want to see how we can actually ensure security by proving it theoretically. So the important question is, how do we define and measure cryptographic security? And there are two aspects to consider this. So first and most importantly is the structural security of the encryption method. By this I mean loosely that an encryption method is considered secure if an attacker has no better way of decrypting a ciphertext than just guessing the secret keys used for encryption. So the method does not offer any backdoors or any weaknesses that could be exploited in a clever way. The second aspect is that the parameters for the encryption algorithms must be right. So the set of possible keys for the algorithm must be so large that even an attacker with a very powerful computer who can make many guesses in a short time will still have only a negligible probability for finding the correct key. So this is called a brute force attack, just trying out different candidates for the keys without any particular system behind it. And yeah, the chance of just finding one in such a brute force attack must be negligible, and that means there must be so many different candidates for the keys that it's just not possible in a reasonable time to try them all. And this is usually ensured by requiring that the keys consist of sufficiently many bits. So if we have an n-bit key, then there are 2 to the power of n possible candidates for the key. But of course, larger keys also increase the computational effort for the encryption algorithm. And as an example, in RSA, the key sizes currently are between 2048 and 4096 bits. And in the past, smaller keys were used, such as 1024 bits, but these are no longer considered secure. And if you use elliptic curves for cryptography, then you can do with much smaller keys. So at the moment, 256 to 384 bit keys are considered to be on a security level that is comparable or superior to RSA. Now, while a large key size protects the encryption method against brute force attacks, we also need other security measures to ensure the structural security of the method. So that was the first point I just addressed. And what this means is that it must not be possible for an attacker to exploit in any way the structure of our encryption algorithm to gain any information about the encrypted message. And this is the notion of semantic security, and informally it can be stated like this. Any information about the plaintext M that can be computed from knowing its ciphertext C can also be computed without knowing C. So knowing the ciphertext C must not give an attacker any information about the plaintext. And in that case, we say that the encryption method is semantically secure. And to rigorously prove the security of an encryption method, we formalize this idea of semantic security in a hypothetical challenge to an attacker. And the challenge is as follows. So we assume the attacker has reasonable computational power. Then the attacker is given 2 plaintexts, M1 and M2, and must decide to which one of these 2 plaintexts a given ciphertext C belongs. And there are different variations of this challenge for different degrees of security. And in these variations, we allow the attacker access to different kinds of additional information. For example, the attacker could have access to arbitrary encryptions of plaintext or to arbitrary decryptions of ciphertexts, other than the challenge text C, of course. And if we can prove that the attacker cannot make this distinction here, better than just randomly guessing which one of the two it is, then we consider the encryption method secure. But how do we prove that an encryption method is secure? The ideal that we long for is to reduce our encryption problem to some other problem of which we know that it is computationally hard, or at least of which we suspect very strongly that it is computationally hard. And for the actual proof of security then, this has to be cast into the attacker challenge for semantic security or one of the variations. Now, I go on a little algorithmic digression, so I will get into some superficial theory of algorithmic complexity and how hard a problem is from a computational perspective depends on how the computational complexity rises with larger input data. Now, the input data could be the number of bits in a key or the length of a list that we want to sort or something similar. And by complexity, I simply mean the time that is used to run an algorithm to solve this problem, or the processor cycles that are required, or the number of elementary operations. So there are different measures. They're all essentially equivalent. They're all proportional to one another. So that's why usually the complexity is only measured in a rough sense. And we only look how does it change if the input data grows. We're not interested in precise numbers because they could depend on whatever unit we take to measure the complexity. We say an algorithm A runs in polynomial time if the computational complexity, which I denote by T of A, of this algorithm A, is bounded by a polynomial function of the size n of the input data. So for example, if TA, the computational complexity for A, is less or equal to n squared, or less or equal to n to the power of 50 minus n to the power of 8, or something similar. So some polynomial expression here that bounds the complexity of the algorithm. And if an algorithm runs in polynomial time, then we consider this algorithm to be efficient. And we do that because polynomial algorithms usually can be run on a real computer in reasonable time, which means we live to see the results of the computation. So it's not some exponential growth in the complexity depending on the input data. And we say that a problem is in the complexity class P if the most efficient algorithm to solve it runs in polynomial time. So if there exists an efficient algorithm by this definition to solve this problem, then it is contained in the complexity class P. And the complexity class NP contains all problems for which a given possible solution can be verified in polynomial time. So here we're not talking about finding the solution to the problem, but if from wherever we're given a possible solution, we can check, is this indeed a correct solution, yes or no? If we can do that in polynomial time, then we say this problem is in the class NP. And of course, verifying a possible solution and computing a solution are two quite different things. And if you wonder about the name NP, this stands for non-deterministic polynomial. And that is because this definition here is equivalent to saying that a problem is in NP if the most efficient algorithm to solve it runs in polynomial time, but on a non-deterministic computer. So non-deterministic, it's a bit of an awkward naming here, but what it essentially means is that in each step of the computation there could be multiple possible outcomes, and we think of it as all of these outcomes appearing simultaneously and being run simultaneously. So yeah, the computational power, at least in theory, is much greater here. And this means that P, the class of efficient algorithms, is a subset of the class NP, because every deterministic computer can be considered as a trivial case of a non-deterministic computer. So that means these algorithms here are contained in NP. And currently the most important open question in computer science is whether this subset relation here is strict or not. So whether P equals NP or P does not equal NP. So this would probably be the more surprising answer, and it would mean that all these problems described here could actually be solved efficiently on a deterministic machine. But the operating assumption for practically all of computer science is that they're not equal. Now, what does it mean to reduce one problem to another? So suppose we are presented with two problems, P and Q, and we assume that from wherever we know that any algorithm to solve P or Q requires at least the computation complexity TP or TQ in the case of problem Q. Now, if there exists an algorithm B that transforms the problem P into an instance of the problem Q, then any algorithm A that solves Q can also be used to solve P. How do we do this? We take our problem P, apply the transformation B to it, so B of P becomes an instance of the problem Q, and then we can apply the algorithm A to it. So this computes the solution of the problem P after we transformed it into an instance of the problem Q. And in this situation, when we can do this, we say that problem P can be reduced to the problem Q. And we use this notation for short. So the symbol here, which is reminiscent of the less or equal symbol in the natural numbers. So P can be reduced to Q. And using this symbol here is motivated by the intuition that Q is at least as hard to solve as P. So that means any algorithm A that solves Q requires as an computational effort at least the same complexity as we would need to solve P. However, there's one thing to be careful here about. Now, from this reduction here, we have that the computational effort of P is less than the computational effort of A and B combined. Okay, because here we use A and B to solve P. And if TP is the minimal effort required to solve P, then this has to be less or equal to the sum of A and B, of the efforts, the complexities of A and B. Now, we assume we have an efficient algorithm A to solve the problem Q, so that was what we assumed about A. So we can replace T of A by TQ. But for us to say that the effort for solving Q is at least the effort of solving P, this part here must be negligible. So our intuition that I formulated here is only justified if the computational complexity T of B that we use for reducing problem P to problem Q, if this computational complexity does not significantly exceed that of TP. Otherwise, the reduction to the problem Q would actually make the situation worse, and we would have to do more work doing it this way. Now, we consider the complexity T of B for the reduction negligible if T of B is polynomial in the input size. So if B is an efficient reduction algorithm. And in this case, we use this notation here. We write an index P for polynomial on this reduction symbol. So P reduces efficiently to Q. And in this case, we can say that our intuition is correct, that solving Q is at least as hard as solving P. Well, because it wasn't, then by reducing P to Q, we could find an algorithm to solve P that was actually less than the minimal effort to solve P, which is a contradiction. Now, there are many important algorithmic problems in the class NP for which no efficient algorithm is known. That's why we suspect that the class NP is in fact not identical to the class P. And you might have heard of some of these. That's the traveling salesman problem, the Hamilton cycle problem, the bin packing problem, and yeah, many others. There are some hundreds of them that are known, or maybe thousands. If it were the case that P equals NP, then for all of these problems there would be some efficient algorithms to solve them. So efficient meaning running in polynomial time. The idea is now, if we were to prove this, to find a single problem P to which we can reduce all the problems Q that are in the class NP. And then show that this problem P actually lies in the class P. So this problem can be solved efficiently. And since we can reduce all the problems Q in the class NP to this efficient problem P, it would follow that all of them must be in P themselves. So that would imply P equals to NP. And this motivates the following definitions. A problem P is called NP hard if it is at least as hard as all the problems Q contained in NP. This does not mean that P itself is contained in NP. It could be even harder than everything that's contained in NP. And the class of these problems, of NP hard problems, will be denoted by NPH. And now we say a problem P is called NP complete if it is both NP hard and if it itself is contained in NP. And the class of NP complete problems is denoted by NPC. So NPC, you can think of it as the set of the hardest problems in NP, because every other problem in NP can be reduced to these NPC problems. So all of them are at least as hard as any problem in NP. Here I have a diagram to illustrate this situation. Now, under the assumption that P is not equal to NP, and the arrows mean that the problem Q1 can be reduced to problem P. So the red one, the class NP, contains P as a subset. It contains NPC as a subset, which is the intersection of the NP hard problems with NP itself. So here P is an NP problem, which is NP complete, so any other problem in NP can be reduced to it. And there are problems that are not contained in NP, but all problems in NP could be reduced to them. So this is this problem X. And yeah, we are right now not so interested in these problems, but yeah, NPH is not a subset of NP, so this is just to illustrate that. Now, if we assume that P does equal NP, the situation looks like this. We have NP equal to P equal to NPC, and all of this is contained in the NP hard problems. So the distinction between NP, P and NPC becomes irrelevant if those two are identical already. But of course there could still be problems that are harder than anything that could be solved with polynomial effort. And many of the classical problems in NP that I just listed are in NP complete. So are there any problems in NP that are not known to be NP complete? So is NPC indeed a proper subset of NP? Well, of course we don't know if it's a proper subset because we don't know if P equals NP, but we can suspect that it is, because there are some problems of which we do not know that they're NP complete. For example, the integer factorization problem, where we compute the prime factors of an integer number. This is clearly in NP because we can easily verify that a solution is correct. So if we're given the prime factors, we just have to multiply them and check if they give the given integer number. But if we're just given the integer number, finding the prime factors is very difficult, and the fastest known algorithm for that has sub-exponential runtime relative to the size of the given number. And another such problem, of which we don't know if it's NP complete, is the discrete logarithm problem. So here we're given this generator G, and we're given G to the power of A, and the question is to find A. And how difficult this problem is depends a little bit on the group, so the arithmetic domain in which we take our element G here. But in the case of elliptic curves, the fastest known algorithm also has sub-exponential runtime, and here it's relative to the number of points on the curve. Now, back to cryptography. How do we apply these ideas to proving security, or at least to try to prove security? For example, as I've mentioned before, RSA encryption relies on the difficulty of the factorization problem. So in RSA we have an integer n, that's the product of two primes p and q. And if we could determine these two, then we could break RSA. So if we can solve this problem, then it would be easy to compute the secret key D from the given public keys, because we know this number n, and here we have this random element E that we picked. And if we could factor n in this way, then the extended Euclidean algorithm would give us an efficient way of determining this secret key D from RSA if we have this information. But prime factorization is assumed to be a very hard problem, as I just explained. The best known algorithm is sub-exponential. And for large n, this means the factorization is not solvable in a reasonable amount of time. And it's similar for the Diffie-Hellman key exchange. This relies on the discrete logarithm problem. And as I just said, the problem here is if we're given the publicly known generator, which is part of the protocol specification, and the power of it, g to the power of a, find the element a. And yeah, here it's very easy. If we can solve this problem, then we can find one party's secret key a, and in this way find the shared secret, because we have g to the power of b, which we can find by listening on the public channel. And if we for some reason find a, then we can compute this, and this is precisely the secret key in Diffie-Hellman. And again, fortunately, it's suspected that this is very difficult. Also, I just explained that before. Here, at least in reasonable groups, such as elliptic curves, computing discrete logarithms is also a problem that, to the best of our knowledge, requires sub-exponential runtime. And yeah, sub-exponential actually means it's almost exponential runtime. It's a little bit below that, but it's much, much more complex than polynomial runtime. So what we've just seen is that RSA can be reduced to the factorization problem. That means here RSA reduces efficiently to factorization, and Diffie-Hellman can be reduced to the discrete logarithm problem. So Diffie-Hellman reduces efficiently to discrete log. But if you've paid some attention, this is actually not what we want. This is no good for our security proofs, because it means that factorization is at least as hard as RSA. But that doesn't really tell us anything about how hard RSA is. RSA could be much, much easier than factorization. So what we actually want are the opposite reductions. So if we want to prove formally that RSA and Diffie-Hellman are difficult to break, we would actually we would need that factorization reduces to RSA and discrete logarithm reduces efficiently to Diffie-Hellman. But unfortunately, neither of these are known to be true. So what is the state of RSA and Diffie-Hellman then? It turns out that the security of the two most used cryptographic algorithms merely relies on the fact that many smart people have tried for a very long time to break them and did not succeed. And that's maybe putting it somewhat cynically, because, as you can imagine, there's a lot of very, very sophisticated research that went into the analysis of these algorithms. And if we assume that factorization and RSA are of the same difficulty, and we assume that P equals NP, then you can actually prove that RSA and Diffie-Hellman achieve semantic security, at least for, well, let's say a suitably tuned version of RSA. And still, security proofs are important because they show what assumptions the security of a cryptographic method is based on. So at least we're not completely staggering in the dark, but we know precisely what the open questions are in the security proofs. And so we can reduce studying security to studying these assumptions, such as these here. And there are also other methods where security proofs by reduction do actually exist, but practically all of them rely on the assumption that P is not equal to NP. So this is in fact a very, very crucial assumption at the heart of cryptography and computer science as a whole. And in the last part of this video, I discuss a new threat emerging to cryptography, which is quantum computing. Quantum computers were first proposed by the mathematician Yuri Manin in 1980 and the physicist Richard Feynman in 1981. So usually Feynman is attributed with conceiving quantum computers, but I think Manin should get some credit too here. And the ideas back then were motivated by the difficulties of simulating even small quantum physical systems with a classical computer. So the quantum computer would be based on the principles of quantum mechanics, and in this way should be able to better represent quantum systems and thus provide efficient simulations of them. Things got interesting in 1985 when David Deutsch gave the first formal specification of a quantum computer and suggested that quantum computers might be superior to classical computers for solving some problems unrelated to quantum physics. And in the 90s, the first problems were posed that a quantum computer could solve significantly faster than a classical computer, but they have no practical use and are mere proofs of concept. Now, the killer application for quantum computers appeared in 1999 when the computer scientist Peter Shor devised an algorithm where quantum computers significantly outclassed classical computers in two important practical problems that we have discussed here: factoring integers and computing discrete logarithms. And this put quantum computers on the map, because a powerful quantum computer could break the most common public key methods that are currently in use. So needless to say that there's a great interest in obtaining such a powerful quantum computer. In classical computing, the state of a computer is at every moment determined by the states 0 or 1 of all the combined bits making up the memory and the registers of this computer. Now, in quantum computing, things are a bit different. So we don't have bits, but they have been replaced by qubits, which obviously stands for quantum bits. And such a qubit has two base states, similar to the state 0 and 1 for a classical bit. But we denote them in this somewhat strange notation here. This comes from the Dirac's bracket notation from quantum physics, and I'm not going to explain what the motivation behind this notation is. That would lead much too far afield and doesn't really make sense if you don't get into the mathematics of quantum computing. So let's just accept this weird notation here. So this is called a ket, not as in the animal, but K-E-T, as half of a bracket. And we call this 0 and 1 to be reminiscent of the classical bit values 0 and 1, but here 0 and 1 are not to be taken as the values of the qubit. It's just some identifiers to distinguish the two base states. And the state of the qubit is a superposition of these two base states. So alpha times state 0 plus beta times state 1. And that means both of these base states contribute to the state of the qubit with certain probabilities that are given by these coefficients alpha and beta here, where alpha and beta are certain complex numbers that together, if you take the absolute values together, add up to 1. So that's a restriction on these superpositions here. And the probabilities with which state 0 and state 1 contribute are the absolute value of alpha squared and the absolute value of beta squared. And you know, the superposition is basically the same as in the thought experiment of Schrödinger's cat. So for Schrödinger's cat, we have two states of the cat, namely the living cat and the dead cat. And yeah, a two-state system in quantum physics is basically nothing but a qubit. So instead of calling them 0 and 1, we might just have called these states alive and dead. Operations in quantum computers are provided by so-called quantum gates. And mathematically, these can be expressed by a certain type of linear transformations, which take this superposition here and transform it into a different superposition. So these probabilities, alpha and beta, are changed by the quantum gate. And now a quantum program consists of the application of several such quantum gates to one qubit or to more qubits, if our quantum computer has more than one qubit. And due to the superposition of the states, this is like applying all these operations to all base states simultaneously. And in a somewhat ironic twist, the laws of quantum physics actually make it impossible to infer the actual state of the superposition. So to make sense of any quantum computation, we have to find some clever way to exploit the side effects of the quantum computation to get some result out of it. So that's an additional difficulty when designing quantum programs. And of course we want to have more than just one qubit if we want to do reasonable quantum computations. So say we have n qubits, and the states of an n-qubit quantum computer are superpositions of the base states derived from the n qubits. So this means we take the individual base states of the n qubits and combine them into joint quantum states, which gives us 2 to the power of n base states. So here I illustrate that for n equal to 3, where we have 8 base states. And yeah, they're given just by combining all the base states from the 3 individual qubits in every possible combination. To harness the full power of a quantum computer with more than 1 qubit, the qubits must be entangled. This is a very important property of a quantum computer. And this means it must be possible for the quantum computer to represent any possible superposition of these joint base states. So in our example with 3 qubits, this means we have all of these superpositions here, where we have all of our 8 base states and each of them multiplied by some complex number, and where all the possible values for these coefficients alpha, beta, and so on can appear. I'm not going into which values are admissible here, so it's not like you can plug in any arbitrary complex number as a coefficient here, but all of them that such that their squared absolute values give you a probability must be allowed to appear in such a superposition. And if your quantum computer can represent all of these states, then you have full entanglement. Now there's the notion of the quantum speedup. So for a given problem P, we refer to the quantum speedup to mean the difference in the computational complexity for a quantum computer as compared to solving the same problem on a classical computer. Then the term quantum supremacy is used to describe the capacity of a quantum computer to achieve a significant quantum speedup over any classical computer for solving a certain problem. And at the moment there is still an ongoing debate on whether quantum supremacy has been achieved for certain simple problems. 2 algorithms promise significant benefits of quantum computers over classical computers. That is Shor's algorithm that I mentioned before, which can compute discrete logarithms and factor integers into their prime numbers, and Grover's algorithm, which can search through unordered data. Other applications usually concern specialized problems in quantum physics or chemistry, or so-called quantum optimization problems. It's important to note that not every problem can be solved more efficiently on a quantum computer, so it is unlikely that quantum computers will eventually completely replace classical computers. More likely, we will have quantum modules built into our classical computers, just like we have graphic cards or math coprocessors nowadays. Now let's see how quantum computers are a problem for cryptography. Shor's algorithm uses a quantum algorithm called the quantum Fourier transform, combined with some classical number theoretic methods to compute integer factorizations or discrete logarithms. And at this point I really have to say Shor's algorithm really is a testimony to human ingenuity. It's an absolutely brilliant algorithm. I can't get into the details here because it's, I would say, quite mathematically advanced. at least much more advanced than what I want to talk about in this video. But I just tell you about the effects. So if a given number is represented by n bits in its binary representation, then Shor's algorithm requires less than n to the power of 3 steps to compute the factorization. And this means it runs efficiently as compared to the classical sub-exponential algorithms. So here we have a polynomial expression in the number n of bits, so this means we have an efficient quantum algorithm. And this enables Shor's algorithm to break practically all currently used public key methods. RSA for any reasonable key length, even ones that are much larger than those currently in use. You could break Diffie-Hellman key exchange and any method that is based currently on elliptic curves. Now, as for private key encryption, there's also an attack. So those methods based on the advanced encryption standard can be attacked by Grover's algorithm. And Grover allows searching in an unordered list with n elements in something that is proportional to the square root of n steps. So this is the order of magnitude of steps that you need to search in an unordered list with n elements, as opposed to the classical order of n steps. So classically you would think in a list that is completely unordered, there's no better way of going through it than just start at the beginning of the list and search through it until you find the element that you're looking for. But yeah, indeed, on a quantum computer you can have a square root speed up, a quadratic speed up. But this speed up is not so significant and can simply be countered by doubling the key length for the advanced encryption standard. So this is a very simple solution, and therefore private key cryptography is currently not threatened by quantum computers. But public key cryptography is. So the threat of quantum computers creates the need for new public key methods that can resist attacks by quantum algorithms. And this kind of cryptography is referred to as post-quantum cryptography. And these new methods must, of course, be based on new computationally hard problems that cannot be solved efficiently by quantum computers. And one thing that is important to note is that post-quantum cryptography itself does not require a quantum computer for its implementation. So the post-quantum cryptography can easily be implemented on classical computers. Only the attacks require a quantum computer. So let's look at some of these quantum hard problems. The first category are coding problems. So these are taken from algebraic coding theory. So the question is, how do I efficiently encode some set of symbols and alphabet in binary numbers, and can use some clever math to do this in a very efficient way. And here the problems are based on the difficulty of reconstructing a message from a noisy encoding. So you have encoded your message, but maybe there's some error in the encoding, or that by transmitting it there was some noise added to the encoding, and you want to reconstruct the original message. And this is actually not such an easy problem. And this difficulty is used in the classical McEliece cryptosystem. So this has been around for quite a while actually. But it was not used on classical computers because compared to other methods, such as RSA, it's actually quite inefficient. So there was no point in using it. But it turned out to be safe against quantum computer attacks. So it has a new lease of life. The second category, probably the most promising one, are lattice problems. These are very similar to coding problems. And here the problems concern determining the points in an infinite discrete set in some space, which are called a lattice, and you want to find the point that is closest to a given point. So I have this little picture here to illustrate this. So our space here is just the plane R2. The lattice consists of all these red dots, which are arranged in this regular pattern, and you should think of them as extending to infinity in all directions. And now we are given this point x, and the question is find the closest point in the lattice. In this case, it would be this point V here, the closest point to the given x. It looks very easy in this little drawing here, but if you have a very high dimensional space, it actually becomes a really difficult problem. And as I said, this seems to be the most popular approach at the moment. And there are several methods based on lattices that have been developed, such as NTRU or learning with errors. So learning with errors is actually also derived from certain coding problems. As I said, they're quite similar. And NTRU is a bit more number theoretic in its ways, and I can't really tell you what NTRU stands for. I think there's not really an official definition for this abbreviation, and people just call it NTRU without bothering what the letters here mean. And another approach is to use elliptic curves again, so-called elliptic curve isogeny problems. But here we use completely different problems than we did in the classical elliptic curve cryptography, and these are much more mathematically advanced. So yeah, I can't really explain what this is about. However, the practicality of these methods is questionable. They have not been so well researched, and one of its most promising cryptographic schemes, called Cyc, was very recently broken. Actually, it was just broken in August 2022 when it was submitted in a competition for the National Institutes of Standards in the US to determine the next generation post-quantum cryptography standards. And I mentioned at the very beginning of this video the advantage of having open cryptographic schemes, because this is what you can do. You submit your cryptographic scheme and then practically everyone can have a go at it. And in this case, someone really found a way to break this cryptographic scheme. And a few of these post-quantum cryptographic methods actually have already been adopted in practice, and notably, perhaps most notably, OpenSSH from version 9.0 onwards uses a combination of classical elliptic curve cryptography and an advanced version of the NTRU post-quantum encryption. So they use both to be doubly safe. So they use a well-established and well-researched classical method and new implementation of a post-quantum method. The idea being, of course, that if it turns out that this is not secure after all and could maybe be broken even by classical algorithms, then they still have the well-regarded classical method in place as a fallback. Overall, from a theoretical point of view, post-quantum encryption suffers from similar problems as the classical ones. In many cases, there are no proofs that breaking the encryption is as hard as the problems that they're based on. Unfortunately, this is the case for the lattice-based cryptography. So we know that the lattice problems are hard, but we only suspect that the encryption problems are just as hard as the lattice problems that they use. Finally, let's see how urgent this threat from quantum computers is. Will there be quantum computers soon? No, there won't. Thanks for watching. Bye. All right, maybe I should elaborate a bit more on this. So let's not stop just yet. Quantum computers do already exist, but only ones with very, very limited capabilities. And I think of them as mere proofs of concept, and they do not really serve any practical purpose yet. And the reason is obviously that it is very difficult to build quantum computers, especially with many entangled qubits. So guaranteeing entanglement of qubits is a particular difficulty of building them, even though there are many different technical approaches how to build quantum computers. So at this time in 2022, when I make this video, it appears that quantum computers that are capable of breaking cryptography are still at least decades away, if not centuries. But perhaps they still arrive soon enough to completely compromise the Bitcoin blockchain. Just kidding. By that time, Bitcoin won't be worth anything anymore anyway. So no worries there. The currently functional quantum computers have only a handful of entangled qubits and are often designed to only solve a very specific task. And quantum computers with unentangled qubits can have more qubits, but they are only suitable for very specialized tasks unrelated to cryptography. And if you want to break cryptography, you really need a general purpose quantum computer with entangled qubits. When reading about qubits of actual quantum computers, for example in the propaganda statements of the likes of Google or IBM, it is important to distinguish between logical qubits, which express the computational power of the computer, so the actual qubits that you can use to model your algorithms on, and the real physical qubits, whose number is much higher usually, and they are needed due to error correction. So you need to have a certain redundancy in your qubits for the computer to function properly. And as I mentioned before, realizing qubits in an entangled state is very difficult to achieve physically. And to realize one logical qubit, one requires 9 physical qubits due to a certain error correction mechanism, which, by the way, was also devised by Peter Shaw. And as a result of this, published qubit numbers are often multiples of 9 or close to multiples of 9 if one of the qubits breaks. So take that into account when reading about qubit numbers. If you have 54 qubits, for example, that could well mean you only have 6 logical qubits. And that reflects the true computational power. And it is actually expected that as the number of total qubits grows, so of logical qubits, that more and more physical qubits will be required to guarantee some redundancy for the logical qubits. Currently, it's estimated that around 50 logical qubits could be enough to run quantum physical simulations or chemical simulations. But to break contemporary RSA encryption, you would need several thousand logical qubits, and that does not even take into account the possibly growing number of physical qubits required for error correction. So, that's the state of the art with quantum computers and cryptography. We're at the end. Thank you very much for watching, and do not forget to like and subscribe.